Hi, I think you are doing well. So, in my last video, what I told you, if you can remember that, I told you that this result is showing some problems because the SPP and code is not the same as the paper. So, in the paper, you can see that this is the core mode and this is the SPP mode, but our result is not showing the same result actually. So what we have to do, we have to check where we just made some mistakes. So for that, I can check physics. So here you can see, okay, I think there is no problem. Uh, and materials is okay. Okay, gold and light, everything is okay. And it is okay. So maybe the problem is here for perfect image. Okay, so here you can see that we select light as a perfect image layer, but this is not perfect image layer. Perfect. This is actually the perfect image layer. This is the analyte. Okay, so we made mistake there. So that's the thing. So this is our analytes, and okay. So now we can simulate it. Um, Okay, so let me check the mesh size, it's normal. Okay, we are searching font for 10 number of modes, so let's simulate it again. Okay, just wait and see how it's working actually. So we'll try to just reproduce this figure today. So that's how we will understand uh, just perfectly we can reproduce this kind of figure. So just stay with me. And then after that, day by day, we'll try to reproduce all the figures. But yeah, yes, it's you know that it's very time consuming to reproduce all the figures, and it's repetitive work kind of. So what I will do for you that I will reproduce two or three conformant loss curve, and then I will from that I will calculate uh, resonance wavelength, amplitude sensitivity, and figure of merit um, to make you understand how actually you can calculate amplitude sensitivity, wavelength sensitivity, figure of merits, and and then I will also explain something with you that how you can just optimize your sensor. Okay, so I think the simulation is done. So like, oh yeah, here you can see that the result is perfect right now, right? So this is the core mode. Okay, so if we change the color as the paper, so here from here you can sense, right? This is the color uh, paper actually showing, right? Let's check. Okay, okay, this is the color actually the paper is showing. So I think it's kind of perfect. Not that much perfect, but yeah. So the figure is not, yeah, it's very perfect with the paper. Okay. So and then we will see the SPP mode. So I think this is the SPP mode, right? Yeah. Uh, this is the SPP mode. Okay. So that's the thing. So I think we got the um, resonance at resonance wavelength. We got the SPP and okay. So the question is, I think you do have a question like how I got sure that this is the SPP mode of the core mode. Okay. So the answer is very simple. Okay, let me explain actually. So, okay, we can start from here. So here you can see that this is a mode, but we don't want to work on this mode. Uh, not this mode, not this mode, not this mode. Okay, this is the Y polarized mode. Okay, so you can see that Y polarized light is also working. Maybe this is not the resonance wavelength for Y polarized light, but yeah. This is mode. Okay, this is the explorers mode. Okay, let's see. Here you can see that this is the light. How light actually interacting the with the plasmonic material at the uh, at the core mode. Okay, so this is the core mode, and light is interacting with the plasmonic material like this. Okay, so see, this is the SPP mode, and uh, here you can see that in at the core mode, maximum light is passing through the core. Okay. If you can see that, if it is white, then uh, there is the maximum light intensity. Okay, so maximum light is passing through the core, and some of light are interacting with the plasmonic material. But in the SPIP mode, what will happen actually? It will not change the it will not change the shape of light actually. So you can see the shadow of the light. Here you can see that this is kind of core mode light, but the light intensity here is very low at the SPP. But the shape is exactly same of the core mode, and the at the uh, uh, the use of gold or plasmonic material, you can see that the shape of the light is exactly same as the core mode, but intensity is very high, right? So that's how you will understand that which one is the core and which one is the SPP. So if you see that, okay, let me show like this. This is also SPP mode, but it's not the SPP of core mode. Why? Because the shape of the light here, you can see that this is not the same as the core mode. Okay. Uh, so if this is on a SPP mode, but not the SPP mode of the core mode that we are working on. Okay. So I think you understand the thing. Okay, thank you. So, yeah, now this is how we will understand which one is core and which one is the SPP of the core mode. Okay, so so now we want to reproduce this. Okay, okay, so we just reproduce this two figure actually. Okay, kind of perfectly. Now we want to reproduce this figure. Okay, so for this figure, this is for explorized light and at a 1.42 refractive index, um, and the simulation is done from 800 to 1200, but it's very time consuming if we just simulate from 800 to 1200. So now for you I can simulate from 900 to 1000. Okay, 900 nanometer to 1000 nanometer. That's how we'll get the peak side of the curve. Okay, so we don't need this part. Okay, so okay. So uh, for that, what we have to check? We have to check the refractive index. Let me check. Okay. Previously we select refractive index at 1.42. Okay, it's okay. Now what we have to do? We have to shift the refractive index. For that, we have to. So in study, you have to click right click, then parametric sweep. Okay, in parametric sweep, what you have to do? Okay, you have to click this at sign. Okay, and after that, there is lots of variable you can see here, but we have to select L because here we select in the parameters. Here we know that we select L as the uh, wavelength, right? So that's why we want to vary the wavelength. So we select L as the wavelength. Okay. Then we have to vary the uh, wavelength. Okay. So click here, parametric value list. Then click the range. Okay. So we will start from 900 nanometer. Okay, and the step size will be 10 nanometer. And if you want, you can take a step size like 1 nanometer or 5 nanometer. That will be more accurate. But for now, I am taking 10 nanometer as the step size. So for your case, maybe you can take 1 nanometer. It's a very good. Mm, okay. So then on 1000 nanometer. Okay. So if you choose 1 nanometer as the step size, then your work will kind of very errorless. Okay, but if you check that to 10 step size, then you will not get actually perfect result. Okay, but yeah, you will get the idea. Okay, so okay, and then replace. So here you can see that this is the range of the parameter values. We are changing um, L or the wavelength with the range of 900 to 1000 nanometer. Okay, now we can compute it. Okay, okay, it will take 2 or 3 minutes maybe. So now what we can say that okay, so the main thing is the model is simulating. Okay, the main thing is we are simulating this model and we'll reproduce this model, but the problem is here you can see that from the model, here you can see that they didn't mention the thickness of the PML layer or light layer, so we cannot select it perfectly, but we have to vary the PML layer or light layer to get the exact result. As you can you say that we didn't find the 100% perfect core mode and SPF mode as as paper mentioned. So for that, what you have to do, but it's very kind of 99% is uh, perfect. Okay, but for if you want to uh, get 100% perfect result, then you have to vary the undefined parameters like thickness of PML or analytes. Then you will get maybe 100% perfect result. And another thing is they didn't mention the width of this channel, and also they didn't mention the width of the lower part of the channel. So it's kind of tough to recreate 100% perfectly this model. Okay, but yeah, you can recreate it almost 99% of this model. Okay, 99% perfectly. So that's very okay to get 99% perfect result. Okay, so that is very okay for reproducing a model, because it's very tough to reproduce 100% perfectly some model. Okay, because there are lots of barrier for us, because the I don't know which model of which version of COMSOL they use. Okay, they use 5.5 of COMSOL, but we are using 6.3 right now. You can use 6.2, 6.1 or 6.0. All the models are kind of similar, or 5.4. They are their interface is kind of similar, but yeah, they day by day they just introduce various things, and they um, just they just what they just um, improve their version. So what I actually what the advantages, so some people actually work on a lower version of console. So what the disadvantages of the lower version is that um they took lots of memory when you simulate the file in console actually. And I think I mentioned you before, when you are simulating COMSOL file, please plug in your laptop charger before simulating, because COMSOL may um, down your battery. Okay, it's there's lots of pressure when you simulate COMSOL file. Okay, so to get to safe side, just plug in your charger before simulating. Okay, so we can check the progress. Here you can see that 55% progress is done already. So okay, no worries. So here I can say that I'm simulating with you. I'm not changing anything uh, behind the scene actually. So uh, so if you are facing any problem like in the time of simulation, please verify and yeah, check again and again your values of parameters and geometries or materials. Or sometimes you may have to call you may took a false mesh or physics. So another thing I can say you that taking lower mesh like in this simulation or we choose normal mesh, right? So it's not fine actually. Normal mesh is not fine actually. To get error get errorless result, you must choose finer or fine mesh. Okay, so or extra fine mesh. That's better. But um, for extra fine mesh or finer mesh, they um, took lots of computational time. So as you know, my laptop is very weak nowadays. So it's very tough for me to choose fine or finer or I choose this normal mesh. That's very tough for my laptop actually. So yeah, I think it's almost done. Okay, let me say 82%. Okay, so I also mention you how PCF-based space sensor work, and another thing I can mention you or I can tell you, if you need any kind of help, you can just email me. You will find my email address in the description box. Um, and if you have any project related work, you can mail me. Like you want to reproduce any model or you want to write any paper, uh, for that you can mail me. We do have a group actually. They actually do some kind of research project work. So yeah, you can mail me. I will forward to them and they will did your work actually. So yeah, you can do this kind of thing as well. Okay. If you need any hurry, then you also mention that. Okay. Yeah, I think it's almost done. 97%. Okay. Okay. So, okay. So what we are going to do actually, we are going to reproduce this curve. So to reproduce this curve, what we actually need, we need um, this equation. This is the confinement loss curve actually. So the equation of confinement loss actually, alpha is the confinement loss here. The unit of alpha is decibel per centimeter square. Okay, so it's actually calculate the value value of loss in decibel per centimeter square area. Sorry, length actually. So the equation is 8.686 into k naught. K naught is the constant value. Okay, this is the actually the free space wave number actually k naught. Okay, so free space wave number, and we have to take the imaginary part of an effective. Okay, and then we just change the because we are taking per centimeter square. That's why we have to multiply with 10 to the power 4. Then is the okay. Okay. Simulation is already done. Okay, so let me check another thing. Okay. I think hmm, okay, let me check a thing. Okay, I'm checking the equation of conformal. Okay, I think the paper mentioned it wrong. I don't know. I'm not sure, but let me check. Um, where is the conformal loss equation? Let me check another paper. They must mention actually, but it's not necessarily that they will mention the conformal loss curve. Okay, but usually they mention. Uh, I think this paper. Okay, it's not free. This paper is not free. Okay, then what you can do? Okay, this paper is not also free, I think. Okay, okay, let me check this paper. Photonic Crystal Fiber plasmonic sensor. Okay, this one is not also free. Okay, whatever, we can continue actually. So simulation is done. So here you okay. So because we choose parametric shape, that's why it's showing a different electric field, but we can calculate it from this electric field. Okay, so we have to, what we have to do, we have to just select parametric solution, study one parametric solution. Okay, then plot. Okay, so it's okay. So what we have to do? Okay, so from 900. Okay, so from 900, and we have to find the core mode. Okay. Please took your cursor here, electric mode index, then to shift it, and here is the core mode of the for 900 nanometer, and then you have to change it to up. You have to change it to up, and then it will change the parametric value of upper portion. Okay, and if you make it down, then it will change the effective mode. Okay, so now we want to change the effective wavelength. Okay, that's why I tap. Okay, then change it. So for all the okay, so till now for till 904 sorry uh, 940 nanometer wavelength, the position of the sorry this one is not core mode. Okay, for till 900 and 30 nanometer wavelength, the position of the core mode is kind of from the bottom 1 2 3 4 4. Okay, so we have to take the data. So how we can take this data from here? So here you can see that there is no imaginary part. So someone just can think that there is no imaginary part. So how we can take the imaginary part of the refractive index. So let me introduce you. Okay, so how you can take the imaginary part of effective mode? So here I can show you how you can take it. So from drive values, you have to right click and you have to choose global evaluation. And in global evaluation, you have to choose equation, and from equation, you have to choose electromagnetic wave, and then from global, you have to take effective mode index. Okay, so you choose the effective mode index, and we are not from calculating from study one. We want to calculate from study one parametric solution, and from there, you have to choose outer solution, obviously, and make it up, and then evaluate. So let me check. Okay, so here we take actually 10 modes. Okay, for 900 nanometer, here you can see that 10 mode here appearing. For 910 nanometer, here 10 mode is appearing for 920. So 940, 30. Okay, so what you have to do, we have to, okay, so take it at the bottom. Okay, then we have to, okay, let me check. Oh, sorry. Till 930 nanometer, the position of the effective mode is from the bottom is 4. So 1, 2, 3, 4. So this one. So we have to copy this row. Yeah, row. So then right click and then copy table and headers to clipboard. Okay. So I already made open a Excel sheet, so you can paste it anywhere. Oh, I'm sorry, Control Z. Um, so it's for 1.42 actually. Sorry. Okay. Sorry. Okay. So sorry, copy selection and headers to clipboard actually. Okay. Now you can paste it here. So here you can see that 900, 910, 920, and 930. So you have to select these 3 rows, sorry, 4 rows, and then Control C and click here and right click and paste special. From there you have to click transpose, then okay. There you go. And then you have to write this equation actually. So let me explain this equation. So from the equation, you can see that you have to write minus 8 point, let me clear it. You have to write this minus, obviously. Okay, minus 8.686 into 2 into 3.4. It's actually pi. Into imaginary part of B is actually this effective mode. And then we have to divide it with wavelength into 10 to the minus 7 because the value of wavelength is in nanometers. That's why we are dividing it into 10 to the minus 7. Okay. So this is the effective mode actually. Effective mode. Okay. And this is the confinement loss. Okay. Write this equation here. There is a minus. I'm mentioning it again. Okay. Then write it this equation and then click. Sorry. Okay. Then just scroll it down. You can see this is actually confinement loss, and then we have to collect the data of 940. Okay. Okay, for 940 here you can see this is not the explorized light, so let me find out this explorized light. Okay, this one is the explorized light uh, from bottom, which is the position is 3 actually. Okay, so let me check. Okay, so it's in here. So we have to collect this data from here. So for 940, this one actually from bottom, right? From bottom, this one. So you can click the single cell actually. How? You can right click and copy cell to clipboard. Okay. Then you have to paste it here. Okay, okay, you can scroll it till 1000. Okay, here you can see that the value is 9.54. Okay, sorry. Then you have to collect data for 950. So it's not the data. This one. Oh, no, this not this one. So maybe this one, not this one. So let me find it. Okay. Okay, this one is the core mode. Okay. So the position of this core mode is bottom of this values. Okay. So let me check it for others wavelength. Okay. Okay. For all others wavelength, the position of the uh, effective mode is the bottom of the row. Sorry, of the column. Okay. So you have to select this bottom one and then copy selection and headers to clipboard. Okay, and paste it here. And how, from where? From 950, right? From 950 you have to copy till 1000. Okay, then paste a special, then transpose. Okay, here you go. We got the result, right? So here you can see we can plot this curve actually. Sorry, from here. From here you have to choose this one actually, then it will get a good curve. So this one. Okay. So it's kind of similar as the paper, I think. Let me check. Oh, here you can see in paper actually maximum confinement loss is actually less than 9. Okay, but we got maximum confinement loss actually more than more than 10 actually, because I told you that we didn't select the thickness of analyte and thickness of analyte and the uh, thickness of PML perfectly. That's why it may change the uh, position of the resonance wavelength as well as the value of confinement loss. Okay, so it's okay. It's a perfect actually. Don't worry about don't ever worry about this. So it's kind of perfect. Okay, so if you want to make it more perfect, what you have to do? I told you before. You have to just uh, change the value. Sorry, you have to sorry, from geometry actually. You have to change the thickness of the analyte and the PML. Okay. Okay. So I think I don't have that much time for now to do that. But yeah, you can do that to make it perfect. And another thing you can take actually for gold, sorry, I chose from my previous data, but they in the paper they actually maybe provide this data. Okay, they don't provide. Okay, they don't. Okay, they provide actually. You can export this data to your model. Then you will get a errorless actually result. Okay, that's the thing. Okay, it's perfect. Now we create. Sorry, we reproduce this. Okay, so for the okay, we didn't actually reproduce this data perfectly. Okay, another thing I can mention you that in this paper they actually mention only the Y polarized light, but they didn't mention, sorry, X polarized light. They didn't mention the Y polarized light. But you can calculate the value of Y polarized light actually as well. It's not that much tough actually. So for that, what you have to do, you have to sorry, you have to start from the from 900, and you have to check this is the vaporized light. Okay, so you have to check how far it's go. Okay, so till 930. Okay, so again you have to just evaluate this data. So okay, so what we checked? We checked that till 930, the position of vaporized light is third. Okay, from bottom actually, from bottom third. Okay, so click it and click. Okay, so you can paste it here actually. Okay, so from 900 to 930, Control C, 900 to 930, space special transpose. Okay, so let me write it effective mode for Y. Okay, and this one was for X. Okay, it's perfect. So you can click it. Sorry, you can copy this one to here. So here it's actually changed the position of the wavelength. So this one will be the wavelength. So click it here and okay. Okay. So this one is D2. Okay, it's perfect. And then just score it to 1000. Okay. Okay, perfect. Now what you have to do? You have to find others value for 100. Okay. So, okay. So maybe this one is the, yeah, this one is the, sorry, this one is the core mode for vaporized. Okay. So for 950, the position of vaporized light is fourth. Okay. So this one actually, okay. Control C. Okay. Sorry. My laptop is hanging. You can see, okay. So paste it here. Okay. Perfect. Now, on 950, sorry, 950, we have to search the position of vaporized light. This one, not this one. Okay. Let me search. Okay, this one, sorry, this one. Okay, the position is second. Okay. Okay, now we can check how far it go actually. Okay, so this for this second one is the vaporized light, effective mode of vaporized light. So you can just replace it uh, from 950, right? From 950 to 1000, copy, and then paste special, then transpose. Okay, there you go. You can delete this things. Okay, this is the confinement loss of confinement loss for Y, right? Okay. Okay, from wavelength confinement loss insert. There you go. This is the curve of vaporized light. It's not that much good. I think the position of resonance wavelength is not here. Maybe it's shift this way. Okay. So for that to get the resonance wavelength, you have to simulate more actually. Then you will get the resonance wavelength. Okay. So yeah, but the curve of vaporized light is not that much good. Okay. That's why they actually didn't work on vaporized light. They all actually work only for explorized light. Okay. That's the thing. Okay. Now we can save it. Okay. So this is the thing what we have done here for reproducing. I forgot it. So what I told you that we want to reproduce this graph, then we have to calculate this curve and this curve. This is for explorized core mode, real part of explorized core mode, and this is the real part of explorized core mode. So, sorry, SPP mode. Okay, this is for SPP mode, real part of SPP mode, and this is the real part of core mode. Okay, so now for that, let this curve and let this curve. for that, what I can do, just insert, right click, insert. Okay. So real part of core, real. Okay, real part of core mode. So this is the core mode. Okay, so we have to calculate the real part. So from keyboard, you have to click um, uh, equal, then real, real. So this is the function to calculate the real part from an imaginary number. So how can we get here? So it's the C2 actually. Okay, this is the real part actually. Let's scroll it down. So here you go. This how you will get the real part of. Oh, I'm sorry. Uh, this is not C2. This is actually confinement loss. This is the effective mode. Okay. Okay. From effective mode, you have to get the real part. Okay. And this will be maybe SPP. Sorry, real SPP. Real part of SPP. Okay. I told you how we can calculate SPP mode. So, okay. Uh, draw this curve first, then I will explain actually. Don't worry about it. Okay. Now, for that, this is not the same. Okay. This is actually secondary axis. You have to choose a secondary axis. In secondary axis, because the value of confinement loss is very large than this lights value. Okay. So here you can see that it's showing in this, its value is showing in secondary axis. Okay. Okay. Now we have to calculate the real part of SPV mode. Okay. So for that, I have to go to the model, and what's the easiest way? So for this thing, actually 950 is the resonance weapon. So for that, the easiest way is find out the SPV mode for uh, the core. Sorry, resonance wavelength is the easiest way. Okay. So for 950, we have to find out the resonance wavelength. Okay. For the core mode. Okay. So no, this one. This one. Total 900 550, and then we have to search the core mode. Okay. This one the okay core mode. Oh, sorry. This on the core mode. Okay. So look at this one. Okay, this on the core mode. Okay, and check the real part of this core mode. The real part of this core mode is 1.4483. So the real part of SPP will be very close to this value actually. Okay, 1.4483. Okay, search the thing. Okay, 1.4482. It's kind of actually very close to 1.44383. Okay, then plot. So here you can see that this is the SPP of the core mode. Okay, this is not the SPP of the core mode, but this one is the SPP of the core mode. Okay, so you have to collect the real part of this core mode. You can write it by your hand, by hand. Okay, so check it 1.4482 for 950. Okay, 1.4482 for 950. 1.4482. Okay, and this one is also for secondary axis. Okay. Okay, then what we can see, that then we can just check for 940. So this is not core mode, sorry, SP mode. This is the SP mode. So for SP mode, the effective, the real part is 1.4485. 1.4485. 1.4485. Okay. Okay. And then um, for sorry for 930. This is also the SP mode 1.4487, right? 1.4487. 1.4487. Okay, it's working perfectly actually, and you don't need to calculate other SP mode. So for this side, okay, this one, okay. This one is the SP mode. Okay, this one, no, no. This is the SP mode. Okay. There is no perfect SP mode of this wavelength, but I think this is very close to the SP mode. Okay. So the value is 1.4478. 1.4478. Yeah. 1.4478. There you can see. So, and okay. So for 980, okay, this one actually 1.44, 1.4476, 1.4476, 1.4476. So this is the thing. So it's not that much good, but yeah, because the value of after the 4 digit, there is some other value. So because here you can see that this is very perfect card, because we take actually 1, 2, 3, 4, 5, 6, 6 value after the mm, point. Okay, but here we choose the only 4 value after the point. That's why it's not showing a perfect result. So if you want perfect result, then you have to calculate from global evaluation. Then you have to copy from global evaluation. That's how you will get a perfect result. Okay, so I think I actually. Hmm, okay, okay. From this, actually, what the purpose of this actually graph actually? Okay, so here you can see this curve. Here we are telling that 950 is the kind of resonance wavelength, but no, 950 is not the resonance wavelength. Resonance wavelength is in between 940 and 950, somewhere in between 940 and 950, because here you can see that the real part of SPP and real part of core is mass in between 940 and 950. That's why the position of the resonance wavelength is here. Okay, so uh, that's why I told you that if you just simulate from with the 1 nanometer interval, then you will get a very perfect result. But here you can see that there is, if we tell that 950 is the resonant wavelength, then this is not actually right. This, there is some error. Okay, so that's the thing. So thank you. We just reproduce this figure 2 actually. Then I think next day we'll reproduce figure 3. No, not all this figure, but okay, we'll understand how you can calculate amplitude sensitivity, wavelength sensitivity, figure of merit. Okay, thank you. Thank you for your attention, and yeah, bye bye. Stay safe.